Hello students, welcome to our physics class. Physics in the 8th chapter, heat and thermodynamics we are discussing. Today you are going to watch laws of heat transfer. Please make sure that the previous videos everything you have watched. Laws of heat transfer. We know that every object absorbs radiations from the surroundings as well as it emits heat radiations at all temperatures except 0 Kelvin. Isn't it? So all the objects will be absorbing the radiations from the surrounding and same way it will be emitting the radiations in the form of heat. Example, if you touch someone, they might feel your skin as either hot or cold. You may have experienced that. Your friend used to say your skin is very hot or your skin is very cool. So, hot bodies radiate more heat than the cooler bodies. Hot bodies radiate more heat than cooler bodies. That means a body at high temperature radiates more heat to the surroundings than it receives from it. Similarly, a body at lower temperature receives more heat from the surroundings than it loses to it. Today we are going to learn the Prevost theory of heat exchange. He applied the idea of thermal equilibrium. And according to his theory, all bodies emit thermal radiations at all temperatures above absolute zero, irrespective of the nature of the surroundings. So what Prevost theory states? Prevost theory of heat exchange. Prevost theory states that all bodies emit thermal radiation at all temperatures above absolute zero, irrespective of the nature of the surroundings. He applied the idea of thermal equilibrium to radiation. So what is maybe thermal equilibrium? First I said that hot bodies radiate more heat than the cooler bodies, isn't it? So at a particular time, the rate of exchange of heat from both the bodies will become same. Okay? The rate of exchange of heat from both the bodies will become same so that the bodies are said to be in thermal equilibrium. Understand? So only at absolute zero temperature a body will not emit any radiation. At absolute temperature a body will not emit any radiation, but above the absolute temperature all the bodies emit thermal radiations at all temperatures. So this is about Prevost theory of heat exchange. The next law is Stefan-Boltzmann law. Stefan-Boltzmann law. Stefan-Boltzmann law states that the total amount of heat radiated per second per unit area of a black body is directly proportional to the fourth power of its absolute temperature. I repeat, state Stefan-Boltzmann law. Stefan-Boltzmann law states that the total amount of heat radiated per second per unit area of a black body is directly proportional to the fourth power of its absolute temperature. This can be mathematically written as E proportional to T power 4. So here E is the heat radiated. Okay? And T is the temperature, fourth power of the absolute temperature. So E proportional to T power 4, or else we can write E is equal to sigma T power 4. E is equal to sigma T power 4. Where sigma is known as a Stefan's constant, the value is found to be 5.67 into 10 power minus 8 watt meter raised to minus 2 K raised to minus 4. Understand? So we have discussed two heat law, that is one is Prevost theory of heat exchange and another one is Stefan-Boltzmann law. in the Stephen Boltzmann law, a special kind is there. That is, if a body is not a perfect black body, we can write the heat radiated, that is heat radiated per second per unit area is equal to small e sigma T power 4. Small e sigma T power 4, where small e is known as the emissivity of the surface. Emissivity of the surface. So what is emissivity? Emissivity is defined as the ratio of energy radiated from a material surface to that radiated from a perfectly black body at the same temperature and wavelength. So what is emissivity? For a perfect black body, we will be writing the Stephen Boltzmann law as only E is equal to sigma T power 4. If the body is not a perfect black body, we are using the formula as E is equal to small e sigma T power 4, where small e is known as emissivity. The emissivity is defined as the ratio of the energy radiated from a material surface to that radiated from a perfectly black body at the same temperature and wavelength. The next law is Wien's displacement law. Wien's displacement law. Actually, it relates the wavelength and temperature. Wavelength and temperature. So in this universe, all the objects emit radiation. The wavelength of these radiations depend on the temperature. The wavelength of the radiation, the distance of that radiation, depends on the absolute temperature. So, radiations have different wavelength and all will emitted. Wavelength will not have the equal intensity. Okay. So, we can say the Wien's law. Wien's displacement law or Wien's law states that the wavelength of maximum intensity of emission of a black body radiation is inversely proportional to the absolute temperature of the black body. So beginning itself I said Wien's displacement law relates the wavelength and the temperature. So the wavelength of maximum intensity of emission of a black body radiation is inversely proportional to the absolute temperature of the black body. So wavelength is inversely proportional to the maximum wavelength is inversely proportional to the absolute temperature. So lambda m is proportional to 1 by T, or else lambda m is equal to B by T, where B is known as the constant. B is equal to Wien's constant. The value was found to be 2.898 into 10 power minus 3 meter Kelvin. From this formula, we can understand the wavelength and the temperatures are inversely proportional. So, if the temperature of the body increases, the maximal intensity wavelength decreases. That means it shifted to lower wavelength. Understand? If the temperature of the body increases, lambda m will get lower. That means the maximal intensity wavelength, lambda m means wavelength, the maximal intensity wavelength shift towards the lower wavelength. If the wavelength is low, frequency will be high. Okay. So let's understand this from a graphical representation given in your book. Look at this figure. Wien's displacement law. X-axis wavelength in nanometer. 0, 500 nanometer, 1000, 1500, 2000. And in the y-axis, radiation intensity. Okay, radiation intensity. So when they plot a graph for different temperature, we will get a structure like this. For a 3500 Kelvin, we got a graph in this manner. For 4000 Kelvin, this is the graph. For 4500. So, with the increase in temperature, we are getting different curves. From this graph, the peak of the wavelength. Peak means the maximum displacement. Okay. So peak of the wavelength is inversely proportional to temperature. 3500, the peak is less. Okay. Sorry, the 3500, the peak value is somewhat a big range. When we increase the 4000 temperature, 4000 Kelvin, the peak value becomes narrower. And 4500, it is narrower, the peak becomes narrower. 5000 and 5500, the peak becomes very narrow. So what do you mean by this? The peak of this wavelength is inversely proportional to temperature increases, the maximum intensity decreases. So this curve is known as black body radiation curve. The graph between wavelength and radiation intensity. The curve, it is clear that the peak of the wavelength is inversely proportional to the temperature, and the curve is known as black body radiation curve. Now there is a point given, Wien's law and vision. That is vision. Vision means what we are able to see. So with the help of our eye, we can see the visible wavelength alone. We know that sun will give the electromagnetic spectrum. It will emit radio waves, microwaves, UV rays, IR rays, etc. But among that, we can see the visible light wavelength. Why our eye is sensitive to only visible wavelength? The visible wavelength actually in the range of 400 nanometer to 700 nanometer. Why this visible light alone we can able to see? Let's see the answer. Consider the sun. Sun is actually taken as a black body. Okay, it emits all the radiations above 0 Kelvin. Now, the surface temperature of the sun is 5700 Kelvin. When we substitute this value in our Wien's displacement law, that is lambda m is equal to B by T. So, B value already I said 2.898 into 10 power minus 3 Kelvin, and temperature 5700 Kelvin. When we substitute, we will get the answer approximately 508 nanometer. 508 nanometer. So this range we can able to see. According to the sun spectrum, the radiations emitted by the sun lie between 400 to 700 nanometer. Okay. So 400 to 700 nanometer, which is the visible part of the spectrum. So 508 is the visible wavelength. So in the sun spectrum, we can see the range about 400 to 700 nanometer. So this range only the visible light is available. Look at this figure, wavelength and radiation intensity. So for a 5700 Kelvin, we got a curve like this. Here, these areas we can able to see. It is of the order of 400 nanometer to 700 nanometer. So accordingly, the lambda value, if you are plotting, we will be getting this peak. So our eye can able to see only this kind of light. Look at this figure. This is actually the frequency, gamma rays, X-rays, ultraviolet, visible light, infrared, radio waves, and here the wavelength are given here. Okay, so wavelength this side increasing, this is high frequency, frequency gets decreases. So here these wavelength we cannot able to see. Only this, that is this area we can able to see, that can be known as a visible spectrum, which is of the order of 400 nanometer to 700 nanometer. Wien's law and human's vision. So we can understand human can see the visible light. That means human eye is sensitive only for the visible light, not in the X-rays or not in the infrared rays. In case if the human had evolved in the other planet, like near the star Sirius, then they were able to have the ability to see the ultraviolet rays. Okay, so this is about Wien's law and vision. So far we have seen law of heat transfer, isn't it? What are the laws we have discussed? Prevost theory of heat exchange, then Stefan Boltzmann law, again Wien's displacement law. Let's move on to the next topic, thermodynamics. Thermodynamics. Here we are studying about the heat, temperature and its properties, isn't it? So thermodynamics is the branch of physics which describes the laws governing the process of conversion of work into heat and conversion of heat into work. Thermodynamics is the branch of physics which describes the laws governing the process of conversion of work into heat and conversion of heat into work. Actually, the laws of thermodynamics are explained over 3 centuries by various scientists: Boyle, Charles, Bernoulli, Joule, Kelvin, Carnot and so on. Okay. So the law of thermodynamics is one of the essential branch of physics. In our day-to-day life, the functioning of everything around us and even body is governed by law of thermodynamics. Okay, so it is essential and it is important to study. Let's see first thermodynamic system. What is meant by system? It is actually a part of the universe, a special part or a finite part of the universe. It is a collection of large number of particles specified by certain parameters called pressure, volume and temperature. The remaining part of the universe is called surroundings. Both are separated by a boundary. Okay. So what is thermodynamic system? It's a collection of large number of particles, in the sense atoms and molecules, specified by certain parameters called pressure, volume and temperature. The remaining part of the universe is called surrounding. Both are separated by a boundary. Actually, this is thermodynamic system. So this is a system, a part, and remaining part is surroundings. So this is the boundary. The system may be either liquid or solid or gas or radiation. Some of thermodynamic system is given, example is given with the surroundings. Let's see that bucket of water. If bucket of water is taken as a system, then open atmosphere is the surrounding. Air molecules in the room, so that will be considered as a system, and outside air is considered as a surrounding. Human body as a system means open atmosphere as a surrounding. Fish in the sea is the system, means sea of water is the surrounding. Understand? So this is about the concept of system and surrounding. Now, there are 3 types of thermodynamic system. Let's say that they are open system, closed system and isolated system. What are the different types of thermodynamic system? Open system, closed system and isolated system. Open system can exchange both matter and energy. For example, boiling water without a lid. Without a lid, if you are boiling the water, what will happen? The energy will be exchanged to the surrounding as well as the matter particles. The molecules of that water also gets exchanged with the surrounding. So both matter and energy can exchange. So without a lid, if you are cooking, there will be a change in matter as well as energy. So this is called open system. Closed system, exchange of energy but not matter. Closed system can exchange only the energy but not matter with the environment. That is, frying pan cooked by the lid is closed. If you are cooking that particular pan with the lid is closed, their energy only will be exchanged with the surrounding, but the matter particle will be in that container. So, but not exchange energy but not matter. Energy only will be exchanged with the surrounding, but matter particles will not be exchanged. Isolated system. Isolated system can exchange neither energy nor matter with the environment. That means there is no exchange of energy and matter with the environment. The best example is thermo flask. Flask, you all know that if you pour the chill water or the hot water, it will long so many hours. That means it will not exchange its heat to the surroundings. So the heat, the hot water, if you pour, the hot water will stay for a long time. Isn't it? When you open and pour it, it will be hot. If you are pouring the cold water, it will long stay. So it will not exchange any energy or matter. So these are three types of system. Thermodynamic system, open system, closed system and isolated system. Let's see the thermodynamic state variables. So in mechanics, we are having the variables as velocity, momentum, acceleration, etc., which will be used to understand the state of the moving object, isn't it? But thermodynamics, what are the state variables? Thermodynamics, the state variable or the state of thermodynamics is represented by a set of variables called thermodynamic variables. For example, pressure, temperature, volume and internal energy. Okay, so in thermodynamics, state of a thermodynamic system is represented by a set of variables called thermodynamic variables. Here the pressure, volume, temperature and internal energy, these values variable. Okay, these are called state variables. That means the values of these variables completely describe the equilibrium state of the system. But heat and work, they are not state variables, they are process variables. Okay, these are state variables, these two are process variables. Anyway, in thermodynamic variables, there are two types. One is extensive variable, another one is intensive variables. Extensive variables, it depends on the size or mass of the atom. Extensive variables depends on the size or mass of the atom. For example, volume, total mass, entropy, internal energy and heat capacity, etc. are known as extensive variables. Okay, it depends on the size or mass of the atom. The total size or the mass can be changed. Then intensive variable. So obviously it does not depend on the size or mass of the atom. Okay, intensive variable, it does not depend on the mass or size of the system. For example, temperature, pressure, specific heat capacity, density, etc. They will not depend upon the size or mass of the system. So this is about two types of variables, extensive variables and intensive variables. Anyway, thermodynamics variables means the thermodynamic state can be represented by means of a variable. That is thermodynamic variables. Here, intensive and extensive variables we have discussed. Continuation with, we are going to learn the equation of a state. Equation of state. The equation which connects the state variables in a specific manner is called equation of state. The equation which connects the state variables in a specific manner is called equation of state. Actually here, this equilibrium, thermodynamic equilibrium is completely specified by the state variables by the equation of state. Suppose if the system is not in thermodynamic equilibrium, we cannot specify the state of the system. So when there is an equation of state, we should understand the concept of thermodynamic equilibrium. Thermodynamic equilibrium is completely specified by the state variable by the equation of state. The two examples of equation of state is given. One is an ideal gas obeys the equations PV is equal to NKT, which is at thermodynamic equilibrium. An ideal gas equation which obeys that PV is equal to NKT. What do you mean by this? Here, we cannot change one variable alone. That means, if we push the piston of a gas container, the volume of the gas will decrease, but the pressure will increase. Okay? So, if we use the piston, the volume of the, if you push the piston, volume of the piston of a gas container decreases. If the volume decreases, the pressure will increase. Clear? If we supply the heat to this gas, temperature will increase, pressure and the volume of the gas also increase. If you apply the heat, temperature will increase, automatically pressure and volume of the gas also will increase. So what does it mean? We cannot change one variable alone. Okay? All the macroscopic variables are connected by this relation. Similarly, another example of equation of states called is van der Waals equation. That is, the real gases actually obeys the van der Waals equation at thermodynamic equilibrium. Real gases obey this equation. The air molecules in the room also obey the van der Waals equation. Okay, so these are the examples of equation of state. Let's move on to the next topic. Zeroth law of thermodynamics. The zeroth law of thermodynamics states that if two systems A and B are in thermal equilibrium with the third system C, then A and B are in thermal equilibrium with each other. So, zeroth law of thermodynamics states that if two systems A and B are in thermal equilibrium with the third system C, then A and B are in thermal equilibrium with each other. Listen here. Consider three systems A, B and C. Okay. So, each systems will be kept at different temperatures. Now, assume that A and B are not in contact. Okay, not in contact with the third system. But A is thermally contact with the C as well as B thermally contact with the C. Now, after a long time, the A and B are kept in thermal contact. After certain time, A and B are kept in thermal contact. What will happen? There will be no flow of heat between the system. What do you mean by this? It implies that A and B are also in thermal equilibrium with each other. Understand? Once the three systems are thermal equilibrium, there will not be any heat flow between as they are in same temperature. Can you understand? Beginning, A and B are not in contact. A is thermally contact with the C, B is thermally contact with the C. So what will happen? A is thermal equilibrium with the C and B is thermal equilibrium with the C separately. After a long time or after a lapse of time, when we put A and B together, there will be no heat exchange happens because A and B are also in thermal equilibrium with each other. Okay. So once the three systems are thermal equilibrium, there will not be any heat flow between them. They will be in the same temperature. That means we can write as TA is equal to TC and TB is equal to TC. It implies that TA is equal to TB, where TA, TB, TC are the temperature of the systems A, B and C respectively. So temperature actually which is used to determine the system whether it is in thermal equilibrium or not. Okay. So the zeroth law also enables us to determine the temperature. Zeroth law enables us to determine the temperature. For example, when a thermometer is kept in contact with our human body, this thermometer shows some readings. How it shows some readings? It reaches actually thermal equilibrium with our body. Our body's heat will be transferred to that temperature, the thermometer. At this condition, temperature of the thermometer will be the same as that of the human body. Understand? So this principle is used in finding the body temperature. So this is the use of zeroth law of thermodynamics. Actually, it is used to find the temperature. So when we are getting fever, we used to check the temperature using thermometer. The principle used is thermometer is thermal equilibrium with our body. So it shows the same temperature what the human body has. Understand? Okay, students. Today we have discussed about law of heat transfer, thermodynamic system and zeroth law of thermodynamics. So you should learn state Stephen Boltzmann law, what is Wien's law, and what is thermodynamic system. Give examples. What are three different types of thermodynamic systems? What is meant by thermal equilibrium? What is meant by state variable? Give example. What are intensive and extensive variables? Give example. What is an equation of state? Give an example. State zeroth law of thermodynamics. Also explains Wien's law and why our eyes are sensitive only to visible rays. So these are the book bag questions we have completed today. So mainly short answers. Please learn the statement properly. Thank you, students.